We have another way to view our molecules with their stereochemistry, and that's called a Fischer projection. Now, a Fischer projection is usually used to show carbohydrates with their asymmetric centers because they typically have several. But it can be used for any compound with an asymmetric center. So a Fischer projection is a flattened out way to show the four groups around an asymmetric center. So you see here is an asymmetric center. This is an sp3 hybridized carbon. We still have a carbon at every end and bend. It's just this time it's an intersection. So here we have our carbon, and our four groups are our alcohol, an ethyl, a methyl, and a hydrogen. Now when you view a Fischer projection, keep in mind that the horizontal groups are coming out towards you. So if you can visualize the vertical groups being in a plane and the horizontal groups coming out towards you, you can probably see these a little bit easier. Now, for the first several times you work Fischer projections, I strongly recommend using the model kit. So if I have the model as it's written, I have the hydrogen to the rear, the OH group in front, the carboxylic acid group on top, and the methyl group to the right. The way that the instructions say is that I'm supposed to hold it by the methyl group. Now when I do that, I'm going to rotate around the sigma bonds and until my asymmetric group substituents are pointing out towards me. Then I'm going to flatten the molecule. Now if I do this too much, it'll pop apart. But I'm holding it by the asymmetric carbon and flattening it out. So you see my carboxylic acid group is on the bottom. My methyl group is on the top. My OH is over here on the left. And my hydrogen is on the right. So on paper, it looks like this. Now notice that I have the same groups as on the perspective formula. And I would assign them the same priorities. OH is number 1, H is number 4. I have to go through the same CIP priority rules to decide that the carboxylic acid group is going to be number 2 and the methyl group is going to be number 3. Now in this case, I'm going to rotate counterclockwise. In a Fischer projection, because group number 4, or when group number 4 is on a horizontal and you rotate counterclockwise, that becomes an R asymmetric center. Now that's backwards from the CIP priority rules because of the orientation of group number 4. When group number 4 is on the horizontal, a counterclockwise rotation is an R group. If 4 is on the vertical, then the rotation is clockwise is an R. So when 4 is vertical, it's the same as the CIP rotations. When it's horizontal, it's opposite. So you might want to keep that on a sticky note near you or write it down in your note sheet for the quiz, because that's a tricky thing we're going to need to keep in mind. So here we want to name this molecule and we want to draw the Fischer projection. So here I'm going to count my carbons first. So I have a pentane. But rather than just a pentane, I have this aldehyde group here on carbon 1. So I'm going to erase the E and add Al. So it's a pentanal. I have 1, 2, 3, 4 alcohol groups. They become a prefix. So this is going to be 2, 3, 4, 5 tetrahydroxy pentanal. But I have asymmetric centers. I have asymmetric centers at carbons 2, 3, and 4. So I need to assign some priorities. I'm going to start with carbon 2. OH gets priority 1. The implied hydrogen is priority 4. Here I have a carbon that has a hydrogen, an OH, and then another carbon. Here I have a carbon that's going to be looked at as if it has 2 O's and 1 H. So I'm going to mark out the atoms that are the same and look to the atoms that are different. So oxygen is going to win over carbon. So The aldehyde is going to be group 3, group 2, where the rest of the molecule becomes group 3. So this rotates around to the right. This is an R. Carbon 3 has similar grouping. I also need to analyze my atoms of difference. So I'm going to mark out the atoms that are the same. Now this carbon will only bond to other hydrogens, so the right-hand side is going to get the higher priority. The hydrogen is pushed back. This is a left-hand rotation, so this is 3s. And for carbon 4, again, similar priority assignments. Here I have a COH. It has 2 H's. Here I have a COH also with 2 H's, with 1 H, excuse me, and a carbon. So H carbon, OH. Differences between a hydrogen and a carbon. The right side is going to get the higher priority. The left side will be number 3. So I'm going to rotate to the right, so it'll be a 4R. Now to draw the Fisher orientation, I'm going to put that aldehyde up high and draw my carbon chain. Now I have 1, 2, 3 asymmetric centers, so I'm going to have 1, 2, 3, and then the rest of the molecule here. So the question becomes, which side do these OHs end up on? So here I have the molecule as it's drawn. I have the aldehyde group to the right. All of my OH groups are coming out towards me, at least the ones on carbons 2, 3, and 4. And then the OH group on 5 is in plane with the rest of the chain. So to make this a Fisher representation, I'm going to hold it by the aldehyde group. And I'm going to rotate all of those bonds so that the substituents on each carbon are pointing out towards me. So you can see with the 3 asymmetric groups, I have alternating sides for those OH substituents. So when I write that Fisher projection, I have an OH alternating. It starts on the right and moves to the left. Now for each of these asymmetric centers, priority number 4 is on the horizontal side. I'm going to go through and just double check that I have them in the right way and name them with the Fisher orientation. This is carbon 2, this is 3, this is 4. So on carbon 2, priority 1 is going to be the OH group. 2 is up here, 3 is down here. I rotate to the left because number 4 is on the horizontal. That is an R configuration. For carbon number 3, OH is number 1. The part of the molecule containing the aldehyde is number 2. The molecule that's underneath is number 3. So because that is a right-hand orientation with hydrogen, the 4th priority on the horizontal, that is an S. And for carbon number 4, we have hydrogen being number 4. OH is number 1. The side that contains the aldehyde is number 2. And the remainder of the molecule down towards the bottom is number 3. Because we turn left on the Fisher orientation, number 4 on the horizontal, that makes 4 an R. So we can double check that we have everything projected correctly with the name. So this is 2R, 3S, 4R, 2, 3, 4, 5, tetra, hydroxy, pentanal.